Welcome to Sandbox, your program, using FreeBSD's Capsicum. Now, before I jump in, I do want to say that even though this talk... Yeah?
Sorry, can I make a quick announcement for the con?
Go ahead, yeah.
And also, can you bring up a web browser?
A web browser? Yeah.
Yeah, if you have it easily accessible.
Yeah.
bsdcan.org. Okay, so there's one thing that Lucas forgot to mention in the schedule. Please. Lucas forgot to mention at the opening thing. On Saturday, in 1160, we have a session called Lightning Talks. Yeah, scroll down a little bit more. Yeah, there we go. Click on that, please. Lightning Talks. So this is an opportunity to give a short, between 5 and 10 minutes presentation. If you're working on something, hoping to recruit others. If you have a short, if you're preparing a talk for a future year, you want to get some quick feedback, or just you're working on something cool, want to share it. This is a chance to go ahead and do that. You do need to sign up by Saturday at 1:30, so just after lunch. Sign up by sending an email to me, or to lightning at BSD-can, and then I'll see how many people are doing it. Divide up the time. We've got 20 minutes. Divide by up to 8 people. And then I'll let you know how much time you have. Send PDF slides to me by 4 p.m., whatever it says on that page. And then I'll merge them all together so we don't have to swap laptops in the middle. And hopefully it'll go really quickly. And yeah, it's a good experience. Also, if you're thinking about doing a talk, maybe you've never given a talk, a 5-minute intro is a great way to do that. Quick questions? No? Okay, thank you very much. Sorry.
You're good. All right. So back to what I was saying, before I dive into the actual content, even though this is called Sandbox, your program using FreeBSD's Capsicum, I do want to point out that I'm going to be tying in a lot of best practice kind of security ideas throughout. So even if you are if I'm going through the presentation and you're like, maybe Capsicum isn't quite for me, at least you'll be leaving this with some kind of idea of how to develop your own program with good security practices in mind. So just, I guess, a +1 here. So a little bit about me. I'm Jake Freeland, and I'm a FreeBSD source committer. And I'm primarily focused on porting software from Linux to FreeBSD and vice versa. I also focus on some compatibility stuff with Linux on FreeBSD. I work at a company called Nixon out of New Jersey, where I manage 100 gigabits per second networking hardware and the drivers that interact with them. And they do live analysis on the packets at 100 gigabits per second speeds. So why should you care about program security? I took this chart from cvedetails.com this morning that shows a trend of the number of CVEs over the last decade. And you can see that 2025 here compared to 2024 is already a little bit more than half of what 2024 was. And it's not even halfway through the year yet. So it looks like the trend of rising CVEs is going to continue this year, and you don't want to be the next CVE or the next big security problem. And the other thing down here is IBM's cost of the data breach report, which they do every year. In 2024, they determined that the average cost of a data breach is around 4.88 million USD. And that was 10% up over the previous year. So security, or bad security rather, is money. And if you want to save money, you should be implementing good security. And Capsicum is one of the good ways to do that. All right, so let's start here with an example problem. Our example problem is going to focus on this kind of relay program that's responsible with communicating to a number of consumer processes. And it acts as a relay between those consumer processes and a physical card. And that physical card has an interface over /dev. Right, so this kind of relay program is probably going to have to be a daemon, because if these consumers start and stop, this always needs to be active in order to relay messages between the two. And the problem with being a daemon is that you're always running. And when you're always running, there's a much longer, I guess, attack time for people to attack your program. So if your program is running as root user or with super user privileges, then this is an especially large problem because you have all the time in the world to be attacked. And if you are attacked, then it's basically root access. And of course, there are caveats to this, or an asterisk, where a daemon might be executing some routine that's not unsafe most of its time that it's operating, and then only once every some time it enters unsafe code. But you get the idea: longer runtime, more exposure to attacks. So how can we protect these kind of programs? The first security model, and probably the most common one, is just don't use any kind of protection. So this would be running as the root user, and running as the root user is a suboptimal model because you're over-allocating resources. You're giving that program access to more than it actually needs to operate. And if an exploit is found inside of that program, then it could potentially lead to code execution, and you could have your entire system compromised because then they have code execution root access, right? So full access to the system. The next security model that I'm going to analyze is POSIX 1000.10e capabilities. And this is just another approach at, I guess, mixing up root privileges into more granular capabilities is what they call them. And these individual capabilities can then be applied to specific processes. So an example of one of these more granular capabilities is the cap_kill capability, which you can give to a process, and then it can bypass permission checks when it's sending a signal, which essentially allows it to send a signal to any process that's on the system. So I have this little analogy down here, this picture. You can kind of think of POSIX capabilities as if your process has a key ring and it starts off with access to maybe two things, right? Then you can use POSIX capabilities to give it access to a few more things, add a few more keys to your key ring. Another model is OpenBSD's pledge. So unlike POSIX capabilities, pledge narrows the execution privilege scope instead of expanding them. So if we go back to the same analogy that I was just talking about with POSIX capabilities, with pledge, you're probably going to be starting as a more privileged user. So that would indicate that you have a larger keychain, you have access to more resources. You can use pledge to lower the scope of what you have access to, or narrow the scope. So then you're taking that keychain that has many keys on it and essentially getting rid of some of the keys, eliminating what you don't need. And that's the, I guess, whole idea here. And then the third one here we have is Capsicum. And Capsicum introduces capability mode, and once a process enters capability mode, it really can't get new resources, at least easily. And the restrictive nature of sandboxes is kind of scary to people. They don't really know how to get at resources once you enter that sandbox, but it offers a very granular protection that you'll see throughout the rest of this presentation. So a little bit of a different analogy here. I have a picture on the left where you have a bunch of little people in houses, and these people can interact with each other, right? This person could go and kill that person. They can really do whatever they want. There's nothing protecting one from the other. But Capsicum is like putting a indestructible wall around you, so nothing can access you, but you cannot access anything, right? So you can see the value and security of this, where you're really isolated from the outside world, but at the same time you need to deal with all the implications of that, right? You can't get research, you can't ask this person, hey, like, do you have an apple to lend me? Do you have some food? You're essentially limited to what you have in that indestructible wall. So now that we know our security options, we can analyze our example problem, go back to it, and identify which models work best. So before I do that, I kind of want to explain in detail what this example problem is doing. So I have an example of a consumer process here, and let's say it writes to a Unix socket, and then the relay program reads from that Unix socket, and then it determines if the request is okay, it will forward it to the device, and otherwise it will respond with failure. And then I use an IOCTL to the dev XYZ to communicate with the actual device. And then on the contrary, right, when the device actually fulfills whatever that request is, then the relay program takes a response from the device. If it's okay, then it can send another response back over the same Unix socket. Otherwise, it can respond with a signal to the process. And then the third circumstance that I put here is it can respond in an arbitrary shared memory region, right? So our example daemon needs to be capable of a lot of different things, which I think is important when you're trying to describe the capabilities of these security models. So I have the requirements, loosely, what this daemon needs to be capable of. So read-write access to the device's devfs entry, read and write access to the Unix socket, ability to send signals, and write access to arbitrary shared memory regions. So now I have a table here, and I'm not trying to indicate that one of these models is particularly better than the other with this table. I don't want to start any flame wars here. But I do want to point out at least what these different models are capable of, at least in the context of this problem, right? So as root, of course, everything's possible. With POSIX capabilities here, I have a list of what kind of capability you need to give to the daemon process in order to perform that kind of operation. And then pledge promises, the same thing here. So you need to remember that this extends the capabilities of the process, and this narrows it. But like with pledge, you give it Unix, then it'd be able to read and write to the device. And then Capsicum here, I have some pre-opening and then Casper sub-processes, which we'll get into shortly. So the next concept that I kind of want to introduce before I get into actually capsicumizing programs is privilege silos. So the thing about pledge and POSIX capabilities is they kind of introduce this notion of grouping different privileges together. And I don't know where I've heard this before, but I've called this privilege silos. And I have some example pictures here of these privilege silos. So POSIX capabilities, they have a capnet admin capability that includes a whole bunch of different operations that you can perform given that capnet admin capability. And say you just need the ability to clear driver statistics, but you don't need the rest of these. With POSIX capabilities, you're essentially giving all of these operations even if you just need one, right? So you're grouping them together. And it's a matter of granularity, right, that determines how much each of these capabilities are providing in terms of, I guess, security looseness. But in general here, you can see that a lot of these capability or silos group together different related calls, even if you just need one. So Capsicum doesn't have this kind of problem because it's a completely different model altogether. That security sandbox or that indestructible wall doesn't use these kind of like granular sections of privileges or these granular silos that they give out. Instead, you just live in a sandbox, and there are ways to acquire resources, which we'll talk about soon. So now we actually get into the actual capsicumization, and capsicumization can be done using cap-enter. It's extremely simple. It's built into FreeBSD's libc. You can include syscapsicum, and you just do cap_enter, and after that, you'll be in capability mode. So I'm just printing from capability mode here. And once it enters capability mode, one, it can't leave, right? And then second, it will not be able to acquire any new resources by itself. So for example, if you try to use the open system call, it will trigger a capability violation and return eCap mode, which is just an error no, right? So now we have a resource acquisition problem. How do we acquire resources? The first solution here is to traditionally just open everything first before you enter capability mode. So you can see as an example here, I'm opening something in my home directory as read-only, entering capability mode, and then I'm still able to read from that descriptor. Essentially, every descriptor that I have before I enter capability mode, I'll still be able to perform I/O on it after I enter the capability sandbox. So if we go back to that indestructible wall kind of analogy, if I acquire a bunch of apples before I build my indestructible wall, I enter my indestructible wall with my apples, and then I build it around me, I'm still going to have what I previously acquired with me in my indestructible wall. All right, so then the next thing I want to point out here is that you can use open-at, or there's a suite of at system calls that FreeBSD has added over time. Open-at, make-dir-at, bind-at are a few examples. And once you enter cap-enter, you can use, or once you enter capability mode, you can use some kind of like reference descriptor with these at calls to then access resources under the domain of that reference descriptor. So in this case, I open a reference directory descriptor, which is my home directory. And I can use open-at with that reference descriptor to access files underneath /home/jfree. So I'm opening home jfree bar here, and this will not fail. Open-at is permitted in capability mode. Whereas if I just tried open without this relative reference, it would be a failure. All right, it's also not permitted to go under the relative reference, right? So if you use open-at with a relative reference like home jfree, you can't use ... and then go into a directory that is outside of the scope of that reference, right? So this would be exiting that kind of reference descriptor scope that you've already acquired prior to entering capability mode. All right, so pre-opening works for very simple cases, but in more complex cases, it does not, because you really don't know what you're going to need in more complex programs. So in this case, I propose that compartmentalization is probably the next best solution. So if you're not able to capsicumize the entirety of your program, at the very least, it is beneficial for you to compartmentalize it or split up the program into several subcompartments that each have their own basic purpose. And when I started the talk, I said that I would introduce general good security principles. I think this is probably the best security principle that I can give to you as a piece of advice. Consider compartmentalization when you're architecting your programs, because splitting up different tasks into different little compartments makes things not only more organized, but also easier to apply these kind of security-focused policies later on. And with the compartmentalization architecture, you can run your unsafe code inside of a Capsicum security sandbox, but run your safe code outside of the sandbox. Right? So I have an example here of syslogd, where I have the actual message processing happening inside of the capability sandbox, because the message processing is generally considered unsafe. But I have a link to a number of other compartments inside of syslogd, like configuration handling, user-provided command execution, TTY message/wall message, that are maybe not, I don't want to say they're safe, but they're things that can't be done inside of the capability sandbox, right? But the most important thing here is I was able to separate these different operations into different compartments. And at the very least, I'm able to put this inside of the capability sandbox, which is one better than not having anything in a sandbox at all. All right, so Capsicum provides a very intuitive interface to, I guess, introducing this kind of compartmentalization and using it with Capsicum. So here's a very quick and simple example of this. I just do a fork here, and I cap enter inside of the child, and then I call a dangerous function in that child, and then I write to a pipe, which then the parent can read from and get the result. Right? So in this case, I'm executing dangerous function inside of the capability sandbox. I know that's unsafe. I'm not executing anything that is unsafe outside of the capability sandbox inside of the parent. Right? So this is something that it can be done extremely easily. And in the case that dangerous function leads to some kind of exploit, now that exploit is running in the capability sandbox and won't be able to access anything outside of the capability sandbox, which minimizes the damage of that exploit. All right. So most compartments may need some refactoring, or most programs may need some refactoring to get compartmentalization working, at least 100%. But you can pick and choose what you want to be sandboxed, and that's the most important thing, right? It's not 0 or 100%. You can put even 10% into it and sandbox the most dangerous things, and that's better than nothing at all, right? And you get a substantial increase in security just by doing that. So some programs were not designed to be compartmentalized, and maybe you just don't want to compartmentalize. So this is where I introduce Libcasper. And Libcasper is another way to acquire new resources inside of the capability sandbox. Well, I say another way, I should just say the first way, or really one of the only ways. So Casper is essentially just a glorified library for inter-process communication with processes that exist outside of the capability sandbox. And you really want to start these processes before you enter the capability sandbox at all, because if you start them once you're in the capability sandbox, they'll inherit the capability sandbox. So here I have an example of connecting to a Casper service. In this case, it's system.net. And the first thing I do is just some boilerplate. I grab a reference token to the Casper service. I use that with cap service open to open system.net, and then I can close the Casper channel. And this channel is just a channel to communicate with the Casper process that exists outside of the capability sandbox. So now in my main process, I can do a cap enter, and then I can call the capnet. It's capnet3. Yeah, okay, I have a reference here. So this is the manual page for it. I can call cap get-attr-info, which is part of capnet3, and that is essentially just get-attr-info, but now I can call it inside of capability mode, which was previously not allowed. And you can see it's just kind of the standard arguments that you would use to get attr info, and then I get a reference back to my attr info. And then I create my socket here, and then I can use cap connect. Again, connect is not allowed in capability mode, so I can call cap connect, and that will allow me to use connect in capability mode. So I have a diagram here kind of introducing what this is like. So if we go back to that people with houses and your indestructible wall, you have your sandbox process here. Opening a Casper process is essentially like opening a channel. I mean, that's literally what it's called if I go to the declaration here, cap channel _t. It's essentially opening a channel to another person or another process outside of your sandbox, right? And I say you're essentially poking holes in your sandbox's walls by doing this. If you somehow find out how to bend this Casper process to your will, then you're escaping the sandbox process. But there are measures in place to at least try to prevent you from doing that kind of thing. So you need to realize the implications that come along with introducing this Casper to your Capsicumized program. So CapNet provides your standard libc networking functions that would usually fail with ECAP mode in capability mode. It's kind of just a convenience library. And the functions that are using Libcasper, which is another manual page which I recommend reading if you're implementing this, functions that use this Libcasper are usually prefixed with cap _ and they can be used inside of capability mode. And they're usually just cap _ and then system call name that's not allowed in capability mode. There are other service libraries similar to CapNet which deal with things outside of just networking that are available, and there's a list on the Libcasper man page of these different kinds of services. All right, so Casper services under the hood. What's actually happening here? These Casper services, they use cap x for nvlist. Nvlist is just a name value list. And here's the function signature of this. It takes a channel, which is just the channel to the Casper service that you want to communicate with. You saw us open that earlier, right here, cap service open. So once you have a channel to the service, you can call that cap x for nvlist with that channel, and then an nvlist. A lot of this is abstracted away from you by the service libraries, but this is what the service libraries are actually calling underneath to communicate with Casper. And this cap x for nvlist takes an nvlist of resources. And here's an example. So this is from CapNet again. This is cap bind. And you can see here it creates an nvlist. It adds a command string. In this case, it's just bind. So cap bind performs the bind command. That's very surprising. And nvlist adds, or I use nvlist add descriptor to add the socket descriptor. You add the attr info here, and then you call this cap x for nvlist. And then that on the other side, okay, well actually, before I get to where this call actually goes on the other side inside of the Casper process, I'm going to say that this is a little bit of a rigid interface. Right here, I'm just using this bind command string. How am I really supposed to know what command strings have what different kinds of arguments? Well, you're not really supposed to know, and because it's all implemented by the actual service library. Again, these things are abstracted from you. So when you're implementing this, you're implementing both sides. This is one side. This is on the side of the process inside of the capability sandbox. But on the actual other side, you have this net command. This is inside of the Casper process. And you can see here, it's really just parsing that command string that we passed into the nvlist. And it's a collection of if, string comp, command, and then string literals. And if they match, then we perform a specific operation. We're essentially passing that NV list in to the operation, and then it will put its output resources in this NVL out. So what I just showed you was capnet's command underscore func. And it has this service, or this prototype here, service command func underscore t, which takes a command, limits the input NV list and the output NV list. And I guess what's really important here is the command. I'll get into limits later. The input NV list is a copy of the NV list passed in that capx for NV list without the command string. That command string is extracted and instead passed as command in the first argument. And then the output NV list, which is what those actual routines that call the operation return their resources in. All right, so all of these things are glued together using the create service macro. And you can see create service here has that command func that I was just talking about. When you call create service, it's essentially just establishing a new Casper service that will be launched at program startup. And you can see here an example. This is, again, capnet. It creates service system.net. It has a limit function, and then it has net command. And I just showed you net command. So this is essentially the entry point to the Casper process every single time the process that's inside of the capability sandbox sends a request over that channel. This function will be called. I know this is like an extremely kind of complicated and rigid interface, but it's just the way that things need to be because essentially you're performing inter-process communication over sandbox walls. So it's a lot more complicated than just your traditional IPC. All right, so limiting a Casper service. I explained this net command, and I left out this net limit. So Casper services are kind of turning into these privileged silos that I talked about, where you're grouping these different kind of similar calls into a single kind of capability almost. And when you open that communication channel, even if you don't want access to call connect and get host by name and get host by adder and get name by info, say you just want to call bind, you're allowing all of these calls, right? Which is the same problem that I discussed before with the privilege silos. All right, let's go back here. So for this reason of making things more granular for the purpose of security, Capsicum, or Libcasper more specifically, introduces a limitation function. And this limitation function, here's an example with capnet, can be used to limit exactly what calls can be made using Libcasper. So you can see this capnet limit and init function, and you can read the man page of cap_net to get more information on this. But I'm initializing a capnet limit item or object with the capnet channel here, and I'm saying I only want to do name to address operations. And then let's just say I want to limit the name to address to only freebsd.org on port 80. And then let's say I want to limit it further to resolution on IPv4 addresses, so I can use capnet limit name to address family. You can see the level of granularity here that capnet provides with its limitation functions that makes it a lot more flexible than these other solutions like pledge and the POSIX capabilities. It's a lot more flexible and a lot more granular, but maybe at the same time it's a lot more complicated underneath. But from the user perspective, you're just using this API, you read the man page, and it just works. So you can then call these capnet, or this capnet limit function to finalize the limitations. And you can specify a limitation function. This is essentially the function that handles how to apply limitations to a service using that limit func inside of create service. Now, I'm not going to get into the specifics of applying these limitations because the reality is each service is completely different in how it handles these Capsicum limitations or these Libcasper limitations. So go look at some examples in the code to get an idea of this, but it provides a lot of flexibility over what you can access, or really what the Sandbox program can access. So here's the path and the source tree to the examples of this. All right. So the recap of this then is functions that are prefixed with cap can be called within capability mode, and they issue commands using capx for envlist to a Casper process outside of the capability sandbox walls, which then allows the Casper process to call whatever privileged operation it needs to and then return resources back to you. The command func is on the Casper side of things, and that is what the Casper process executes when it receives a request from the process in the capability sandbox. The limit function restricts what the service can be used for from the process in the capability sandbox perspective, and then the create service macro glues all of this together. So I know that's a lot, but you can always go back in these slides. I'll post them later and use this. I mean, it took a while for me to wrap my head around all of this too. All right, so you may remember this table from earlier. And in the Capsicum column, I listed Capsicum subprocess under signals and shared memory. And given what you know about the Casper subprocesses and services at this point, you can probably imagine what steps are required to implement this kind of functionality. So we can just run through this real quickly. For signals, let's just use this as the example. Signals, you can create a Casper subprocess that then let's just say it's called cap_kill. That would be the command name that you'd call from inside of the capability sandbox. You'd call cap_kill, which then sends a message using capx for envlist over those indestructible walls to the Casper process. The Casper process then enters its command func, which then string compares and executes the kill system call based on the, I guess, parameters that you sent through it in the envlist provided to capx for envlist. And then it could send whatever response back in the envlist out that you see in command func. All right. So despite the rigidity of these Casper services, they are rigid, I will say that. They provide Capsicumized processes a necessary way to access resources outside of the capability sandbox, because otherwise you're restrained to whatever you had from before you entered. And when used correctly, they can assist in sandboxing very complex processes. All right, so now we're past actually capsicumizing from, I guess, a pure standpoint where you're just modifying your code. Now I want to go into analyzing how you can capsicumize your program easier starting off, right, before you even make any modifications. So when a program is placed in capability mode, it's not really very clear if it's following the rules of the sandbox. If you're performing very good error checking, you'll get errors everywhere saying eCap mode. But this can often be strenuous to fix one error and then recompile the program and then rerun and then run into another ECAP mode error, and then fix that, and then recompile, and then rerun, and then basically fall into that loop of continue recompiling every single time you run into an ECAP mode error. And that's assuming you have good error handling. Luckily, Ktrace 2 was expanded to include the ability to track capability violations even without putting your program in capability mode. And the general way to do this, I've labeled the C calls here, is you can open ktrace.out, and then you can call ktrace on ktrace.out with this KTR FAC cat fail flag. And this essentially goes through all of the different capability violations that the program would otherwise hit when it's executing, and it will log them to this ktrace.out file. All right, so here's an example program. So I have those 2 lines that I just introduced on the previous slide, and then I have a number of different kind of snippets that raise capability violations. When I compile and run this program, I can do a kdump, which essentially decodes that ktrace.out file. And it will tell me a detailed description of all of the different capability violations that were encountered throughout the execution of the program. So this will give you a good idea before you even jump into capsicumizing of what the upfront investment will be to capsicumize your program. How many violations am I really going to have to be dealing with when I'm trying to capsicumize the program? So if you run into a lot of these, it will probably be harder than if you run into a small amount. But I mean, that's not always the case. Some problems are a lot more difficult than others. All right, so violation tracing is just another tool in your toolbox when you're trying to debug Capsicum and capsicumize your program. And it's just a decent starting point. It's not a be-all, end-all utility. It's not going to change your code for you, and it's not perfect as well. I mean, there are some things that, because this KTR cat fail is recording capability violations of a program that's not actually running in capability mode, it may make the program run into situations that it might not otherwise when it's executing inside of capability mode. So it's not perfect, but as a general rule of thumb, it does a decent job. All right, so now we get to, I guess, the overall recap here. Capability mode is just another security model that is designed to make programs safer in the end. And it provides this robust security and isolation from the rest of the system. If it's properly integrated, it's a whole lot better than not having anything at all. But it can be a little bit challenging to implement in the end. But I assure you, based on the statistics at the start of the slideshow, implementing it is, even though it might be a lot of work, it will pay off because you might mitigate some security vulnerability that would cause you a lot of headaches otherwise. All right. So that is the presentation. Thank you for attending, and ask any questions that you may have. Yeah.
Can you talk about the comparative performance implications of Capsicum and how it's capabilities and such?
Performance implications?
Yeah, like how much of a overhead is there with the different methods?
I'd say probably negligible. I mean, Capsicum checks are being performed in most cases anyway, so I don't think there is really any security overhead to running in capability mode. I mean, you may need to re-architect your program, which leads to different kind of performance, but as a general infrastructure, Capsicum doesn't provide any overhead. As for Linux capabilities, I'm not sure what the implementation looks like on the kernel side there, but I imagine it's just like Capsicum where a lot of those checks are already being performed anyway.
Okay, thanks.
Yeah.
You showed an example.
John has a mic for you.
You showed an example of limiting to FreeBSD.org port 80. Is there a pre-made module that does that for HTTPS with certificate checking allowed?
I'm not exactly sure. I mean, you could use 443 here, right, to limit to...
Well, yeah, but I'm concerned about the certificates.
Yeah, I'm not exactly sure, to be honest. If anyone else knows, they can chime in.
I think the typical model would be like this. This allows you to get a socket to that address, but then everything
Yeah.
after that happens in your sandbox. So you don't have like a Capsicum specific module to do anything like that. But then you also have to arrange to validate certificates. Maybe you have to pre-open at-syscalls or something like that first.
Exactly, yeah.
So I don't think we have any comprehensive something that would integrate with it. So at least not.
Yeah, I would say that I think the intent of the Casper services so far has been basically to provide a Capsicum, or the Casper services is to provide a Capsicum-friendly implementation of existing functionality, and then I think this is something that providing higher level services like open a SSL connection to somewhere, I think would build on top of that very, very nicely, and is something that should be provided in a higher level infrastructure, but it isn't part of Casper right now.
So you mentioned that Capsicum itself doesn't add any real overhead. Is there performance impacts of using Casper as a solution just simply because of the way that the...
I'd imagine so. I mean, it's in the end, it's performing inter-process communication. I don't know in what way the low-level details of that. It might be some Unix socket communication. Yeah, John's
just wondering if it's like for certain heavy network things, it might be generally better to just create the socket ahead of time.
Yeah. In most cases, I'd prefer creating the socket ahead of time. I mean, if you can do pre-opening, that is generally preferred over any kind of Casper implementation.
I think usually too, you're using Casper to brief messages over Unix main socket to get the socket, but not for any bulk data transfer.
Yeah.
I think you mentioned at the beginning with the analogy with the guys like in their houses and whatever, that if you're in the sandbox, you can't touch anyone, but also no one can touch you. Does that mean that you can choose to not receive certain signals? How does that work?
That is true, yeah. They can send signals to you. So I guess that analogy may not be perfect. You could still receive a signal from like a privileged process and be inside of a capability sandbox and terminate from it, essentially. Yeah, so I guess it's more of a unidirectional flow where you can't access people outside of you, but people can generally access you to an extent. I don't really know how much more I can add to that.
All right, thank you.
Yeah. All right, well, looks like no more questions. Thank you guys for attending.